So after going through the definition and some elementary properties of the Laplace transform, let's solve some Laplace transform problems. So in this lesson, we are going to solve or find the Laplace transforms of the following function. This happens to be our first question. Let's try to solve this together. So we have I, and then I. So for I, we want to find the Laplace transform of the function sine omega t. Now we know that the Laplace transform of the function sine at is given by a divided by s square plus a square. Now in place of a, we have omega. Wherever we see a, we are going to fix omega. So thus we have omega divided by s square plus omega square. So this is the Laplace transform of sine omega t. Let's move on to the next one. We want to find the Laplace transform of the function sine t. Now the Laplace transform of sine at is given by a divided by s square minus a square. So note the difference. The Laplace transform of sine at is a divided by s square plus a square, and the Laplace transform of sine at is given by a divided by s square minus a square. Now we have a to be 1, that is the coefficient of t is 1. Therefore, we are going to have 1 divided by s square minus 1 square, and then 1 square is still 1, so we have s square, or better still we have 1 over s square minus 1. Now to the third one, I, we are going to find the Laplace transform of the function 2t square minus 3t plus 4. Now we can split this into 3 different Laplace transforms. That's using the property of linearity, or the linearity property of the Laplace transform. We can have the Laplace transform of 2t square minus the Laplace transform of 3t plus the Laplace transform of 4. Now because 2, 3, and then 4 are all constants, then we can pull out the constants so that we have 2 times the Laplace transform of t square minus 3 times the Laplace transform of t plus 4 times the Laplace transform of 1. Now we know that the Laplace transform of t to the power n, where n is a positive integer, is equal to n factorial over s to the power n plus 1, and then the Laplace transform of 1 is equal to 1 over s, where s is greater than 0. So we are going to use these 2 properties in here. So we have 2 times, now this corresponds to this property of the Laplace transform, t square t to the power n. Therefore we have n to be equal to 2. Therefore this becomes 2 factorial divided by s to the power 2 plus 1 minus 3 times the Laplace transform of, now here we have t to the power 1, and that also corresponds to this property of the Laplace transform. Therefore we are going to have 1 factorial divided by s to the power 1 plus 1, and then finally we have plus 4 the Laplace transform of 1, that is 1 over s. Now let's multiply the various constants across. So 2 factorial is 2, that is 2 times 1 is still 2, so we multiply these 2 by 2, and then we have 4 divided by s to the power 2 plus 1, 3, minus 1 factorial is 1, so negative 3 times 1, it's still negative 3, so minus, we have 3 divided by s to the power 2 plus 4 divided by s. Therefore, this is the Laplace transform of the function 2t square minus 3t plus 4. Now let's move on to the second question. So for the second question, we want to find the Laplace transform of the function e to the power 3t times cos 6t. Now we can do this straight away, or we can use the first shifting property. The first shifting property or theorem. So the first shifting property or the first shifting theorem. Now it says that if the Laplace transform of a function f of t is equal to f of s, then the Laplace transform of the function e to the power at times f of t is nothing but f of s minus a. Now you realize that this corresponds to, the question we have. The Laplace transform of this corresponds to the Laplace transform of the question we have. Therefore, we can relate the two so that e to the power at is equal to e to the power 3t. We can say a is equal to 3, and then f of t is equal to cos 6t. So first of all, what we are going to do is to find the Laplace transform of f of t. So the Laplace transform of f of t, which is equal to the Laplace transform of cos 6t, is equal to, now the Laplace transform of cos at is given by s divided by s square plus a square. Therefore, we have a to be 6. So we are going to have s divided by s square plus 6 square. And then 6 square is 36. So we have 36 here. Now the next thing is we want to find the Laplace transform of the function given, which is e to the power 3t cos 6t. Now we need to understand that the Laplace transform of f of t is what we have as f of s. So the next thing is basically to find f of s minus a, and that is the Laplace transform of e to the power 3t cos 6t. So what this primarily means is that wherever we are going to see s, we are going to replace that by s minus a. So we have a here to be 3, therefore s minus a becomes s minus 3. So wherever we see s, we are going to substitute and put s minus 3. So we are going to have s minus 3 divided by s minus 3 all square plus 36. So this is equal to, we have s minus 3 on top, and then s times s is s square, s times negative 3 is negative 3s, negative 3 times s is also negative 3s, so negative 3 minus 3 is negative 6. So we have negative 6s, and then negative 3 times negative 3 is plus 9, and then plus 36. So 9 times 36 is 45, so we simply have 45 here. So this is the Laplace transform of e to the power 3t cos 6t. So now to question 3, we are going to find the Laplace transform of the function 3 sine 2t plus 3 sine 2t. So we know that the Laplace transform of sine at is given by a divided by s square minus a square, and the Laplace transform of sine at is given by a divided by s square plus a square. So for the question given, the Laplace transform of the function 3 sine 2t plus 3 sine 2t, using the linearity property of the Laplace transform, we are going to split this into two Laplace transforms. So we have the Laplace transform of 3 sine 2t plus the Laplace transform of 3 sine 2t. So we are going to pull out the constants. So we have 3 times the Laplace transform of sine 2t plus 3 times the Laplace transform of sine 2t. So using this property, we have the Laplace transform of sine 2t to be, now a is 2, okay, a is 2, so we have 2 divided by s square minus 2 square. Now 2 square is 4 plus 3 times, now the Laplace transform of sine 2t, that is, we are going to use this property. So we have a to be 2, so that's, we have 2 divided by s square plus 2 square, which is also 4. So we multiply the constant across. We are going to have 6 divided by s square minus 4 plus 6 divided by s square plus 4. So let's try to simplify this. So we have the LCM to be s square minus 4 s square plus 4. Now s square minus 4, s square plus 4 divided by s square minus 4. This cancels out this. We are left with s square plus 4. So we have 6 times s square plus 4. And for this, we are going to have 6 times s square minus 4, because this is going to cancel that. So we are multiplying 6 across for each of the terms. So we are going to have 6x squared plus 24 plus 6s squared minus 24, all divided by, now s squared times s squared is s to the power 4. S squared times plus 4 is plus 4 s squared. S squared times negative 4 minus 4 s squared. Negative 4 times 4 is negative 16. So finally, 24 cancels out negative 24. We have 6s squared plus 6s squared, that is 12s squared divided by, this also cancels out that, and then we have s to the power 4 minus 16. Therefore, the Laplace transform of this function is nothing but 12s squared divided by s to the power 4 minus 16. So let's move on to question 4. For question 4, we want to find the Laplace transform of the function e to the power 3t plus cos 6t minus e to the power 3t cos 6t. So we have the Laplace transform of e to the power 3t plus cos 6t minus e to the power 3t cos 6t. So let's split this Laplace transform. So this will be equal to, we have the Laplace transform of e to the power 3t plus the Laplace transform of cos 6t minus the Laplace transform of e to the power 3t cos 6t. Now, the Laplace transform of e to the power at is given as 1 divided by s minus a. The Laplace transform of cos at is s divided by s squared plus a squared, and the Laplace transform of e to the power at cos bt is given by s minus a divided by s minus a all square plus b square. We are going to use all these 3 transforms in here. So we have the left hand side equal to, now the Laplace transform of e to the power 3t. Comparing to this, you realize that a is equal to 3. Therefore, we are going to have 1 over s minus 3 plus, also comparing this to that, we have a to be 6. Therefore, we are going to have s divided by s squared plus 6 squared, and then 6 squared is 36. So we have 36 minus, comparing this and then that, we have s minus a is 3 divided by s minus 3 all square plus b square. Now b is 6, so 6 square is 36. So therefore, this is the Laplace transform of the function given. Now let's move on to question 5. We are going to find the Laplace transform of the function t squared sine 2t. Now with this form of the function, we are going to use the property of multiplying by t to the power n. So multiplying by t to the power n. Now, for the Laplace transform of the function t to the power n times f of t, the Laplace transform is given by -1 to the power n times d to the power n over ds to the power n of f of s. Now what this primarily means is that, first of all, we are supposed to find the Laplace transform f of s, which happens to be the Laplace transform of the function f of t. So from this Laplace transform, we have f of t corresponding to sine 2t, and then we have t to the power n corresponding to t squared. And then from this, you realize that we have n to be equal to 2. So first, let's try to find the Laplace transform of f of t, which happens to be f of s. So we have f of s, which is equal to the Laplace transform of f of t, and that is equal to the Laplace transform of the function sine 2t. Now this is equal to a, so a is 2, so we have 2 divided by s squared plus a squared, and then a is 2, so we have 2 squared, which is 4. Now the next thing is we have the left hand side, okay, the left hand side, which is, the Laplace transform of, so let's have the Laplace transform of the function t squared sine 2t, and that is equal to, using this formula, we have -1 to the power n, and then n is 2, times the square over the s square of the function f of s, which is 2 divided by s squared plus 4. Now we can further represent this as 2 times s squared plus 4 all to the power -1. So let's try to find the first derivative of this function and then the second derivative of this function, and then we multiply that by -1 square. So for the first derivative of the function, 2 times s squared plus 4 all to the power -1. So here we are going to use the shortcut form of the chain rule to find the first derivative of this Laplace transform. So we are going to hold 2, and then we drop the exponent, so that is -1. We differentiate what we have in the brackets. We are going to have 2s, and then we multiply that by what we have in the brackets, s squared plus 4, and then we reduce the exponent by 1. So -1 minus 1 is -2. So this is equal to, we have 2 times -1, that is -2 times 2s, so -4s times s squared plus 4 all to the power negative 2. Now let's try to find the second derivative. So negative 4s into brackets s squared plus 4 to the power negative 2. So here we are going to use the product rule. So first of all, we are going to hold negative 4s and then we differentiate this. So differentiating this, we are going to drop down the 2, the exponent, and then we differentiate what's in the brackets. We are going to have 2s. We maintain what we have in the brackets, s squared plus 4, and then we are going to reduce the exponent by 1. That becomes negative 3. Plus, we are going to hold this, that is s squared plus 4 all to the power negative 2, and then we differentiate that, we have negative 4. So we multiply, so we are going to multiply constants across. So here we have negative, negative, positive. 4s times 2 is 8s times 2, 16s times s, 16s squared. So we are going to have 16s squared times s squared plus 4, all exponents negative 3, and then here we have negative, so minus 4 times s squared plus 4, all exponents negative 2. Now we can express this as 16s squared divided by s squared plus 4 to the power 3 minus 4 divided by s squared plus 4 to the power 2. Now at this point we can find the LCM. So we have the LCM to be s squared plus 4 all cube. So s squared plus 4 all cube, that is the LCM. So this divided by that, we have 1. So 1 times 16s squared is 16s squared minus this divided by that, we are left with s squared plus 4. So we are going to have minus 4 times s squared plus 4. Negative 4 times s squared is negative 4s squared, and then negative 4 times 4 is negative 16. So we are going to have negative 4s squared minus 16. So here you realize that 16s squared minus 4s squared, we have 12s squared, and then minus 16 divided by s squared plus 4 all cube. So this is the second derivative of this Laplace transform. Now we are going to multiply this by 1, and that is still the same expression. So the Laplace transform of this function is equal to 12s squared minus 16 all divided by s squared plus 4 all cube. Now let's move on to question 6. We are going to find the Laplace transform of t to the power 3 over 2. We are asked to find the Laplace transform of t to the power 3 over 2. And then we can further represent this as the Laplace transform of t to the power 1 times t to the power 1 over 2. Notice that 1 plus 1 over 2 is 3 over 2. Because we have the same base, we are going to add their exponents. Now, since we have this, then we can relate this to the Laplace transform of t to the power n times f of t. So which means that we are going to use the property of multiplying by t to the power n like we did in the previous example. So for this, you realize that we have f of t to be t to the power 1 over 2, which is further represented as the square root of t, and then you have t to the power n also given by t to the power 1, and thus we have n to be equal to 1. So how do we find the Laplace transform of the function? given. So first of all, we need to find the Laplace transform of f of t, which is the square root of t. Now, even before that, notice that the Laplace transform of the function t to the power n times f of t is given by -1 exponent n times d to the power n over ds exponent n times f of s. So f of s is the Laplace transform of the function f of t, which is the square root of t. Now the Laplace transform of the square root of t is given by square root of pi divided by 2 times s to the power 3 over 2. This is the Laplace transform of square root of t. Now we can further represent this as 0.5. You know 1 over 2 is 0.5. So 0.5 times square root of pi times s to the power -3 over 2. So this leaves the bottom and then it appears on top. So we have exponent -3 over 2. So that is f of s. That is f of s. So we are going to plug f of s in here. We are going to plug f of s in here. So since n is equal to 1, then we are going to find the first derivative of this Laplace transform. So let's try to find ds of 0.5 times square root of pi times s to the power -3 over 2. So that is equal to, now we are going to treat 0.5 times the square root of pi as constant. So we drop down this exponent, that is -3 over 2. And then mind you, 0.5 is 1 over 2. So times 1 over 2 times square root of pi. And then we still have s exponent. We are going to reduce the exponent by 1. So -3 over 2, which is -1.5, minus 1 is -2.5, which is -5 over 2. Therefore, this becomes -3 over 4 times the square root of pi times s to the power -5 over 2. And that can as well be represented as -3 times square root of pi over 4 times s exponent 5 over 2. So that is ds of f of s. So we plug that in here so that we have the Laplace transform of the function t to the power 3 over 2 equal to -1 exponent 1 times -3 times square root of pi divided by 4s to the power 5 over 2. Negative times negative is positive, so we are going to have 3 times the square root of pi over 4 times s to the power 5 over 2. So for question 7, we want to find the Laplace transform of f of t equals 1 from 0 through to 1, and then f of t equals 0 when t is greater than 1. So the Laplace transform of f of t, which is given as f of s, is equal to, we have the integral of e to the power -st times f of t from 0 to infinity dt. So we can expand this to have, we have first of all the integral from 0 to 1 of e to the power -st, and then we have f of t to be equal to 1, so times 1 dt plus the integral from 1 to positive infinity of e to the power negative st times 0 dt. So because we have 0 multiplying this, it means we are going to obtain a constant at the end, and we don't need that, so we just cancel out this, and then we are left with, the integral of this function. So we have the integral from 0 to 1 of e to the power negative st dt. Now let's try to integrate this. So when you integrate this, you are going to maintain that, and then you differentiate this with respect to t, that is the exponent with respect to t, and you have negative s. Now let's evaluate the upper limit minus the lower limit. So, and then we have inside of the brackets, we are left with e to the power negative st. So in place of t, we are going to substitute 1 and then 0. So for the first one, for the upper limit, we have e to the power negative s times 1 minus e to the power negative s times 0. Now this is equal to, we have negative 1 over s times e to the power negative s minus, now this goes to 0, e to the power 0 is 1, so we have that here, and then we are going to multiply negative 1 across. So if you multiply this negative 1 across, we are going to have 1 over s, and then this becomes negative, so negative e to the power negative s, and then negative negative, it becomes positive. So we can interchange the positions of these two terms so that we have 1 minus e to the power negative s. So that is the Laplace transform of the function given.